just to remind you what we learned last meeting, we learned that the velocity, the actual velocity distribution is not constant. It takes parabola, looks like this. The particle at the middle of the pipe has the maximum velocity, and this velocity is reduced until reaching zero. It's theoretical distribution because we don't have zero, because if you have zero, that means we don't have flow at this contact. But anyway, this distribution, we can represent this distribution using this equation. This equation is a function of the maximum velocity, the radius of the pipe, capital R, and the radius or the distance between the centroid and any point you are looking for. We covered also last meeting that we have two main types of flow. The first one called laminar flow, which is smooth flow. The velocity relatively is low, and water is moving in layers, parallel layers, like this. The second type of flow, which is called turbulent flow, we don't have uniform, or I'm sorry, we don't have a smooth flow. No, we have turbulence inside this pipe, something wrong. So this happened in very high speed, very high velocity. And also we covered a term called Reynolds number. This number will help us to figure out what is the type of the flow. If the value of this number is smaller than 2100, you are talking about laminar flow. If this number greater than 10,000, that means we have fully turbulent flow. If this number in between, we have transitional flow. And this number, Reynolds number, equal V, velocity, time diameter, time rho, which is density divide mu, which is the dynamic viscosity, or equal V time D divide nu. And we have also another types of flow based on the cross section. If the cross section area is constant, that means you have uniform flow. If the cross section is not constant, that means we have non-uniform flow. And also based on the discharge. And the last meeting, I told you what is the meaning of discharge. Discharge meaning we have volume passing through a cross section in a unit of time. The value of this volume passing through this cross section per unit of time can be called discharge, or we can call it flow rate. That means it will be volume unit divide time unit. Probably cubic feet per second, probably cubic meter per second. Based on the discharge, if this discharge is constant, we can call the flow steady flow. If the discharge is variable, a rapid change in the discharge, we have something called unsteady flow, and this flow will cause something called water hammer, and this water hammer can cause damage in the system. Probably explosion in the pipe system will happen. Last meeting also, we covered something called continuity equation. If you have a pipe, and this pipe with cross-section area A, and this pipe has a flow of water inside with velocity v, that means the discharge of this pipe equal area time v. The discharge at any cross section, at this cross section, for example, so the area of this cross section time velocity at this cross section, we can get Q. This value of discharge will be constant through the pipe. So Q equal area V, which is constant. That means if you have this cross section number 1 and you have another cross section number 2, that means Q at this section equal Q at this section. That means area V equal area V at any cross section. Area is the cross sectional area of flow. V is the velocity of flow. Q is the discharge, or sometimes call it flow rate. This point is very important. Please pay attention. If you have main pipe and this pipe is distributed to smaller pipes like this, so guys, discharge at the input, which is Q, which equal area V, area for this main pipe. V is the velocity in the main pipe. For this branch, number 1, number 2, number 3, number 4, we have here area 1, V1 in this pipe. We have area 2, V2. We have area 3, V3. We have area 4, V4. Area 1, the cross-section area for this small pipe. V1 is the velocity inside this pipe. Area 2, V2 for the second pipe. Area 3, V3 for the third pipe. Area 4, V4 for the fourth pipe. Keep in your mind, if you would like to get the discharge in pipe number 1, you have to multiply area 1, V1. Discharge in pipe number 2 equal area 2, V2. Discharge from pipe number 3, area 3, V3, and keep going. Q4 equal area 4, V4. Keep in your mind, because the input must equal the output, so discharge in the main pipe must equal Q1 plus Q2 plus Q3 plus Q4. That makes sense? So area V in the main pipe equal area 1 V1 plus area 2 V2 plus area 3 V3 plus area 4 V4. Does that make sense? That makes sense? Keep it in your mind. The input from this side must equal the output from all of these sides. So discharge at the main pipe equal discharge number 1 plus number 2 plus number 3 plus number 4, and if you have many, so plus all of these branches. Any question so far? Any question so far? If you have only one pipe, I can say discharge here equal discharge here equal discharge here. So Q1 equal Q2 equal Q3, because you are talking about one pipe. So area 1 V1 equal area 2 V2 equal area 3 V3. That makes sense. Any questions so far? Guys, if you have any question, please let me know. Okay, let's do these examples. This example is a very good example. You can find something like this in your FE exam. If you are planning for FE exam, you can find something like this. As I told you, FE exam is a piece of cake, but just you need to be organized a little bit. So we have two pipes connected together. So the first pipe looks like this with diameter 260 millimeter. For some reason, this pipe reduced to smaller one with diameter 130 millimeter with a transition like this. Okay, that's fine. The speed of the fluid is 4 meters per second entering. So at the entrance, we have a speed here, V, equal 4 meters per second. The speed in the 130 millimeter pipe is most nearly. What will be the speed of the fluid when entering the smallest one? Do you expect this speed will be faster or slower? What do you think?
Faster.
Thank you. Guys, when I was young, when I was a child, when I'm playing with a hose and trying to spread the water, if you would like to make this water faster, you need to squeeze this output. Do you remember that? What will happen? We didn't understand what's going on. When you squeeze this output, the cross section is reduced. So the hose looks like this, and you squeezed the output like this. So the output with the area 2 and the remaining hose with area 1. We have here a regular velocity, V1. So we have here V2. To make area 1, V1 equal area 2, V2, so you reduced area 2, that means V2 will be faster. So you can expect faster output. That makes sense? Anyway, so what's going on? I will say this is cross section number 1, this is cross section number 2. Based on the continuity equation, area 1, V1 at the first cross section must equal area 2, V2 at the second cross section, because you are talking about one pipe. This is only one pipe. So the input Q at the input must equal Q at the output. So area 1 V1 equal area 2 V2. Let's do it. I believe I don't need to remind you. For a circle, the area of a circle probably by divide 4 diameter square or by r square. The area of the circle based on the radius by r square, based on diameter by divide 4 diameter square. So keep it in your mind, please. So area 1 will be by divide 4 times 260 square. V1 is 4 meters per second. Area 2 by divide 4 times 130 square times V2. Please keep in your mind, if you are talking about this term equal to this term, keep in your mind the units for area must be the same units for this area. So the unit for this velocity will be the same like unit for this velocity. Because one of you will say, hey, this one in millimeter. That means this area will be in millimeter square. That makes sense. This velocity in meter per second. Do you think I need to make matching of the unit? Yes and no. Yes, because we need all of them in meter or all of them in millimeter. No, if this unit will be the same like this one, because this one also in millimeter, so the unit will be millimeter square. That means the velocity on the other side will follow the velocity on this side. So velocity V2 will equal, also you can cancel by divide 4 by divide 4. So 260 square times 4 divide 130 square. This velocity will be 16 meter per second. Wow. So the velocity originally was 4 meter per second, and the output became 16 meter per second. Any question? Do you have any question? Okay. One more example. One more example. Take your time. If you have any question, let me know. For example number 4, we have a circular conduit. There are different diameter. D1 equal 2 meter. Changes into D2, 3 meter for some reason. The velocity in the entrance profile was measured, V1, 3 meter per second. Calculate the discharge and velocity at the outlet profile. What is the velocity, V2? And what is the discharge at the outlet? We are looking for calculate discharge and velocity at the outlet profile. This is the first part of the problem. That's fine. I believe we have one pipe. So at cross section number 1 and the cross section number 2. Area 1, V1 equal area 2, V2. This is the key to solve this type of problems. What is the area 1? By divide 4 times diameter square 2 square. What is the velocity at section number 1? 3 meter per second. Area 2 by divide 4 times diameter square 3 square times V2. I believe I can cancel this one by this one. So the remaining V2 equal 2 square times 3 divide 3 square. This velocity will be 1.33 meter per second. And that makes sense for me. Why? Because at this smaller pipe, we have velocity 3. At the larger pipe, we can expect slower velocity. So your velocity becomes smaller, 1.33 meter per second. What is the discharge at the outlet? Equal area to V2, area by divide 4 times 3 square, velocity 1.33. Keep in your mind, please, this area in meter square, this velocity meter per second square, they must be consistent. So by divide 4 times 9 times 1.33 will be 9.4 cubic meter per second. That makes sense? That makes sense? If you have two terms are equal, units is not a big deal. You need only this area looks like this one in the unit. That means this velocity looks like this one in the unit. But if you would like to multiply these two terms together, please make your units consistent. This one in meter squared, this 1 meter per second squared. That means the product will be cubic meter per second. We are done with the first part. The second part. The second part of the problem. Determine also type of flow in both conduit profiles. I'm sorry, what you mean by type of flow? Whether the flow is laminar or turbulent flow. We need to determine what is the type of flow in this part, what is the time of flow in the other part. Guys, as I covered before, if you would like to figure out what is the type of flow, laminar or turbulent, you need to figure out what is the value of Reynolds number. So let's do it here. For profile number 1, Reynolds number probably equal VD rho divide mu or VD divide mu. Which one I'm gonna use? Okay, read the problem carefully. The temperature is given 12 degrees Celsius. I don't care. The kinematic viscosity of water. Kinematic viscosity of water. This is nu. So the value of nu, which is kinematic viscosity of water, is given 1.24 times 10 to power negative 6. So I believe I will use this term. Okay. Just a reminder, for profile number 1, the diameter is 2, the velocity is 3. So diameter equal 2, velocity equal 3. Nu is given right now, how much? 1.24 times 10 to power negative 6. Can you tell me what is the value of Reynolds number? Yes, I can. Velocity 3, diameter 2, 1.24 times 10 to power negative 6. What is the value of Reynolds number? Piece of cake, 6 divide 1.24 times 10 to power negative 6. This value will be 4,838,709. Do you think this number is greater than 10,000? I believe yes. So this one will be turbulent fully. Turbulent flow. Profile number 2. The diameter, the velocity for profile number 2, we have D equal 3 meter, velocity equal 1.33 meter per second. Because we have the same fluid, that means nu equal 1.24, the same value, times 10 to power negative 6. So Reynolds number equal VD divide nu. This value will be 3,217,741. I believe this number also is greater than 10,000. So this one will be fully turbulent. So the second part of this problem, we are looking to determine what type of flow, laminar or turbulent flow, based on the Reynolds number. And this Reynolds number is a function of V, diameter, and nu. Nu is the viscosity, is the kinematic viscosity. So it's given in the problem. V and D, we figured them out. So we can determine the Reynolds number. And once you get the Reynolds number, you have a range here. Greater than 10,000, smaller than 100, and in between you can determine laminar or fully turbulent or transitional flow. Any question, guys? Do you have any questions so far? I think this this module is very easy. Any question? Looks good. Okay. As I told you, if you have main entrance, so area V, which is Q at this entrance, and this entrance is divided to two branches, this one and this one. So in this one, we have area V. We have here area V, which is Q1, for example, and this one area 2, V2, which is Q2. Keep in your mind, Q at the main entrance equal Q1 plus Q2, because here we have two branches only. We have two branches. So area V at the main entrance equal area 1 V1 plus area 2 V2. So the total flow rate is the sum of the flow rate in the parallel pipes, like I did here. Okay, so how many branches? We need to add them together, and all of them equal the mean discharge. We have example here. The total flow rate is total means at the main entrance. Q here equal 300 cubic meter per second. What is the flow rate through the 250 millimeter pipe? This one. What is the discharge here? Branch number 2. And we have a given information that velocity in branch number 1 is V1, velocity in branch number 2 is V2. We have a relationship between the two velocity. V1 equal 1.2 V2. Let's see. Do you remember, if you have main entrance and this main entrance is divided to two branches, what do you have? We have Q equal Q1 plus Q2. Does that make sense? So Q is given 300. You are lucky. What is the value of Q1? Area 1 V1. What is the value of Q2? Area 2 V2. Okay, go ahead and put your number. What is the area for branch number 1? By divide 4 time what? 0.15 square time V1 plus area 2 by divide 4 time 0.25 square time V2. Guys, because we have two terms added together, we must make our units consistent. This side in cubic meter per second. The other side must be in cubic meter per second. That means this area must be in square meter. This velocity in meter per second, that makes sense. Meter square and this velocity meter per second, that makes sense. Remember, this diameter is given 250 millimeter, and this diameter is 150 millimeter. We need to convert this diameter and this diameter to be in meter. Divide it by 1000 will be 0.25. Divide this one by 1000 will be 0.115. This is what I did. Okay, go ahead and get a number. 300 equal by divide 4 times 0.15 square. This number will be 0.017 V1. The second number by divide 4 times 0.25 square. This number will be 0.049 V2. This is the first equation. We have two variables, V1 and V2. What do you think? We have another equation which is given by the problem, that V1 equal 1.2 V2. Okay, go back to the question number one. Equation number one. Remove V2. Remove V1 and put 1.2 V2. So 300 equal 0.0117 time V1. Please remove this term and put 1.2 V2 plus 0.049 V2. The only unknown in this equation is V2, so I can figure it out. V2, oh, I'm sorry, wait a moment, 0.017 times 1.2 plus 0.049 divide 300. V2 will be 4,322 meter per second. And V1, you can multiply this number by 1.2. It will be, I have a mistake here, another mistake. I have another mistake. It's a little mistake. It's not a big deal. This velocity is not meter per second. It's meter per hour. Do you know why? Because the flow rate is given 300 cubic meter per hour, not per second. So this one will be velocity meter per hour. This one will be meter per hour. Okay, no problem. Keep it. We must keep our units consistent. That's it. So the velocity from this equation 4,322 is meter per hour. That's fine. Multiply this number 1.2, you can get V1 equal 5,187 meter per hour. Okay, but the problem did not ask you to figure out what is the velocity in pipe number 1 and pipe number 2. The problem asked what is the flow rate, what is the discharge in pipe number 2. Okay, discharge in pipe number 2 equal area 2 V2. Go ahead and put your number. Area 2 by divide 4 times 0.25 square time V2 which is 4,322. Guys, be careful. The area here in meter square, that's fine. The velocity here in meter per hour, that's fine. So the final answer will be cubic meter per hour. I believe this number will be 212 cubic meter per hour. Okay, so the discharge in this site will be 212 cubic meter per hour. I believe 100% that the discharge on this one will be 88 cubic meter per hour. Do you know why? Because if you add this discharge plus this discharge, which is 212, must equal 300. So this one is 212. That means this one must be 88. So the total will be 300. Any question? Guys, do you have any question? So right now, you can start to solve your homework. It's very easy. How to determine the Reynolds number. Question number 1, question number 2, probably question number 3. Starting from question number 4 and 5 and 6 based on the continuity equation.